Behind the ordinary objects which surround us in our day-to-day lives lies something extraordinary. Incredible stories of ingenious solutions to problems most of us never knew existed. So what mysteries are concealed in everyday things we take for granted? Recycling, plasma TVs, fireworks, railway tracks, and ink cartridges. 5 ordinary things, 5 extraordinary stories, now revealed as we go behind the scenes, inside the machines to find out, how do they do it? Ever wondered what happens to old aeroplanes? Bizarre as it may seem, they're turned into mobile phones. That's right, a chunk of these massive old warplanes will soon be a designer slimline cell phone gently vibrating in someone's coat pocket. So how do they do it? Welcome to the Davis-Monthan Air Force Base near Tucson, Arizona. Davis-Monthan is a jet plane junkyard for the US Air Force. At Davis, you can find hundreds of old warplanes from F-4 Phantoms to B-52 bombers, all quietly broiling in the desert sun. This is where old planes come to die. But it's also where they get resurrected into something new. The Lockheed C-141 Starlifter is a troop and supply carrier, once the pride of the Air Mobility Command. After more than 40 years of military service, the Starlifter looks like a tired old warhorse. But to salvage worker Ramon Martinez, the old Starlifter has just what you need to make new high-tech mobile phones. Tons of metal sheeting, miles of wiring, thousands of electrical components. Martinez has already removed much of the plane's interior. All that remains is the shell. In one piece, it's too big for the recycling machine. But Martinez is about to fix that. With Martinez at the controls, a massive excavator comes to life. It's a machine that's normally used to erect buildings and bridges. But today, it's a plane killer. Like a voracious beast, the cat advances on the Starlifter. What follows is not for the faint-hearted. First, Martinez rips off the pods that held the engines. Then, he hacks off the wings, one by one. After that, the relentless jaws of the cat close upon the tail section. Finally comes the fatal blow. Like a predator tearing at its prey, the cat rips out the innards of the stricken Starlifter. It's not pretty. To some, it might seem gruesome, but it's effective. In just 40 minutes, no section of the plane remains unscathed. What's left are not exactly bite-sized chunks, but they're small enough to be carried to the next stage in the plane's transformation. Half a mile away, the Starlifter faces more chomping from more metal mashers. But there's still nothing here that looks like it could be turned into a mobile phone. Time to pay a visit to the Hammerhead Mill. This is an old aeroplane's worst nightmare, where a B-52 finally meets its match. Bits of plane are fed into a rolling mill. Steel spikes mash them up into unrecognizably small pieces. And this is what's left. Thousands of small scraps on a conveyor. But now comes the tricky bit. There are all kinds of components here, made of steel, aluminium, even plastic. Somehow it needs sorting through. And this is how they do it. At the end of the conveyor, a powerful magnet literally sucks iron and steel into a separate hopper, allowing aluminium and plastic to drop directly onto a second conveyor. A manual trawl for unwanted items, another round of grinding and mashing, and what you're left with is the stuff mobile phone circuit boards are made of. It seems hard to believe that redundant bombers and jet fighters find a new life inside your coat pocket. But they're not just in your phone. Believe it or not, the inside of your TV or computer or car radio is just as likely to be made up of old military hardware. 5 ordinary objects, 5 extraordinary stories. Coming up, these new TVs create amazing pictures on a wafer-thin screen. But did you know they work using a kind of cosmic gas? The secret behind plasma TVs. Next on How Do They Do It? We live in an age defined by TV. It entertains us. It informs us. It is our window onto the world. But a revolution is transforming television. Not what's on it, but what's in it. Welcome to the Plasma TV. To make plasma television super thin, you need to harness a fundamental cosmic force. The glass screen is filled with gas, but not just any gas. It's the gas that makes the northern lights flicker in the upper reaches of the Earth's atmosphere. It's the gas that lights the sky with lightning rods hotter than the surface of the sun, and it's called plasma. It's the weird substance behind these natural wonders which is the secret ingredient in ultra-thin TVs. So, how do they do it? It's a rainy day in Miyazaki, South Japan. In this factory, Hitachi make 500,000 plasma TVs every year. This may look like a normal television screen, but look closer and you'll see not one but 2 glass plates clamped together. It's what happens in between that is the secret to the production of the ultra-thin plasma television. Between the plates lies a matrix of 1 million individual and minute cells, each one a fraction of an inch tall. Across the top and bottom layers of the glass are hundreds of thin electrodes crisscrossing one another. Their job is to create an electric environment that charges a mix of inert gases that will soon fill up those cells. The gases are called neon and xenon. Once charged with electricity, they create plasma. Most people imagine there are only 3 states of matter: liquid, gas, and solid. But there's a 4th, plasma. And believe it or not, it makes up nearly all the visible matter in our universe. By charging certain gases with electricity, it's possible to create plasma. And this plasma transmits light. So how do you recreate the northern lights inside a TV screen? First of all, fill it with neon and xenon. This tiny glass tube is fitted to the back of the screen by a robotic welding device. Using the tube, air will be sucked out and a gas cocktail will be pumped in. A short trip to an airtight section of the factory where the gas is stored. This is where chemistry meets engineering. The screens emerging from the chamber are full of gas, but there's one problem. Charged neon and xenon only generate ultraviolet light, invisible to the human eye. The solution? Another clever bit of chemistry. Each cell has been coated alternately with a red, green and blue chemical called a phosphor. So each pair of glass plates now contains a matrix of microscopic electrical wires and a honeycomb of minute cells, each filled with neon and xenon, and now delicately coated in various kinds of phosphorus chemicals. All that's needed to make the plasma do its stuff is the flick of a switch. This technician is creating a kind of electric storm right in front of our eyes. As an electrical charge surges around the components, the screens burst into life, and a plasma TV is born. This explosion of coloured light shows the phosphors and the plasma are working. Now it's the job of the electrical circuits to combine the right cells to produce the right colours.
Plasma can identify 1 million colours. That's more colours than the human eye can recognise. I think plasma is a great technology.
But a TV that runs on gas with a little help from electricity poses peculiar problems. In a normal TV, you don't want faulty electrical circuits. In a plasma TV, you don't want a gas leak. So the screens visit the aging room. In here, hundreds of plasma screens are switched on and left for hours to make sure the chemicals are contained and stable. The plasma screen is working, but there are no pictures yet. There are no tuners, no receivers, no aerials. There's still a plasma TV to be built. Generating sound and vision involves thousands of individual components. Stored on reels of plastic, they're fired at high speed onto circuit boards. High-pressure plastic injection machines produce the various casings for the different sizes of plasma TVs made here. Then everything is brought together on the production line. Circuit boards which control the signal, the power, formats and tuners are all placed on the inner back wall of the TV. But right now the screen has a poor contrast ratio, giving off a kind of milky grey light. So another screen is added to increase the contrast. Then everything is checked again. Colour bars make sure each TV is producing the correct colours, whites and blacks, rather than muddy greys. Test patterns, formats and functions all need to be assessed. These guys at least get to watch the front of a TV screen. Spare a thought for Satoshi Maruono. It may sound like robotic bedlam, but to Satoshi's trained ear, the chirps and squeaks tell him if the TV's working as it should. And some tests involve a highly technical process. He's listening for loose screws. Satoshi sees the back of hundreds of TVs every day, and he'd much rather be watching the front.
I love TVs so much that I make them for a living. I don't have a plasma TV myself yet, but I do dream about getting one.
After packing and boxing, a few TVs are chosen for one last bone-shaking quality check. Every now and again, a television is taken off the line and subjected to a spell in the vibration chamber. A metal floor plate shakes the TV to make sure everything is screwed together properly and that there are no loose parts. When you open your TV's packaging, everything should have been shaken, but not stirred. As the workday comes to a close, the TV sets are loaded onto trucks to be shipped around the world. Box upon box of cosmic plasma destined for your living room. The plasma technology behind your flat-screen TV is now also used in manned spaceflight, as a propellant in spacecraft thrusters. Back in the factory in Japan, the day shift is over and the workers have gone, leaving the plasma sets switched on to dream quietly of the Northern Lights in glorious Technicolor. 5 ordinary objects, 5 extraordinary stories. Sunset over New York. It's July the 4th, one of the biggest dates in America's calendar. Independence Day. Excitement fills the air. New Yorkers make their way to the dockside for a front row seat at one of the biggest shows on Earth. The most gigantic firework display.
All of the world, people love fireworks. Nobody likes it more than the people in New York. We're convinced of that.
For days, a team from Macy's department store has been coordinating a massive operation involving engineers, TV crews, police, and city and government officials.
We deal with so many city agencies and so many people that work for those agencies, outside vendors, volunteers. All told, there's about 5,000 people that need to come together and be on the same page for this.
A lot of effort for one of the biggest shows in the world. The vision of this man, firework designer Gary Souza.
For me, the first few aerial shells that go in the sky, I am just totally thrilled. To me, that's the best moment in the whole show, because then I know that things are going to work.
Souza knows he's only going to have one chance to get this right. By definition, you can't rehearse a fireworks show.
Basically, you get one shot at it, and if it doesn't work, basically sucks.
The Macy's firework display will be one of the biggest and best ever. Yet, no matter how high-tech it all seems, even the most spectacular firework is the product of a very ancient technology. So, how do they do it? The story starts half a world away. In the Chinese city of Liuyong, they know all there is to know about fireworks. Because fireworks is about all this town makes. Indeed, fireworks are so central to the city's way of life that they've even put up a statue to honor them. One of Liuyong's biggest employers is Black Cat. The company manufactures all sorts of fireworks which produce the most exotic effects. But for all the modern packaging, the fireworks we use today remain the products of ancient techniques developed by the Chinese 2,000 years ago, here in the hills surrounding Liuyong. They still make fireworks in these hills, It's too dangerous to do it anywhere else. And this is why. Black powder, the Chinese call it, a blend of charcoal, sulfur and potassium nitrate. By themselves, each of these chemicals is harmless enough, but once they've been mixed, look out. The powder is mixed by day and it's tested by night. Black powder was invented here 2,000 years ago. Put a match to it, and it does this. The potassium nitrate in the mix acts as an oxidizer. In other words, when heated, it creates oxygen to make the other ingredients burn fiercely. But the ancient Chinese alchemists soon discovered something else interesting about black powder. When it's packed into a confined space, like a tube, kaboom. Pyrotechnicians call this effect the bursting charge. The ancients also learned that if you make a hole in the bottom of a firecracker, you can direct the force of detonation downwards. You get what is now called a lifting charge. And that's what makes a firework fly. In the light of day, manufacturing continues. But now we come to the most astonishing secret ingredient essential to making a firework. How do they turn simple rockets into amazing fireworks that perform all kinds of fancy tricks? How do they create the cascades, the clusters, the rings, the starbursts? The secret ingredient is rice. These pellets are filled with gunpowder. The Chinese call them pearls, and they're made from dried rice husks which have been coated with a slow-burning mix of powder and glue. The pearls stop the gunpowder from exploding all at once. To get multiple effects, pack the pearls into spheres called shells. To get different colours, add different kinds of mineral salts. Strontium for red, barium for green. To get sparkle, add flakes of aluminium. Link the shells to the main charge by time delay fuses. Light the rocket, and you'll set off a spectacular chain reaction. Each wave of rice pellets ignited by the detonation of the previous wave. No matter how big or complex, all fireworks are based on this simple chain reaction effect. All you have to do is use more rice and different kinds of shell. July 4th, Manhattan. As darkness falls, anticipation builds. It's showtime. Back at the control center, the countdown begins. In a few short moments, the team here will unleash a barrage of high explosives across the city's skyline. Quite suddenly, it begins. At a rate of 1,000 shells a minute, the team launches a staggering 40,000 tons of high explosive into the sky. It's a truly awesome spectacle. The technology may be 2,000 years old, but there's still nothing to beat a firework display.
I love the fireworks the best. There's just something magical about them. This was the event that caused me to want to do events for the rest of my life.
An amazing sight. And it all comes down to a bit of chemistry, a lot of rice, and a simple chain reaction. On July the 4th, thanks to Gary Souza and his team, and an age-old technology from China, New York City celebrates American independence with a bang. 5 ordinary objects, 5 extraordinary stories. Coming up, the rail track. It's the secret behind rapid mass transit. Next, on How Do They Do It? They call it a cathedral to industry. But it feels like the gateway to hell. It's big, it's hot, it's noisy, and makes something many of us use every day without even thinking. Rail tracks. But these are no ordinary tracks. These are the longest railway tracks ever made. At 120 meters apiece, these tracks are designed to serve Europe's high-speed rail network. High-speed rail networks carry trains at phenomenal speeds, around 350 kilometers per hour. That's equivalent to a Formula One racing car on full throttle. Normal tracks can't cope with the stresses and strains high-speed trains impose. Too many welded joints between sections of track, too many sharp bends. To make the journey smooth and safe, you need fewer welds and gentler curves. And that means making single sections of track the length of a football field. So, how do they do it? The story starts here, deep in the heart of the Austrian Alps. The gingerbread houses and snow-capped mountains may seem an unlikely location for heavy industry. But it's this spot that Austrian rail giant First Alpina has chosen to call home. The tracks are born in a furnace. Steel ingots cooked at a searing temperature of 1,400 degrees centigrade. In this heat, impurities in the steel float to the surface and can be cleaned off. But how do you clean a red-hot chunk of steel? As they emerge from the furnace, the fledgling tracks face a violent baptism. A cleansing, a dousing in a high-speed jet of water. The process is called descaling. The steel is so hot, the water literally explodes on contact. Descaling is spectacular. It's also practical. The explosive force has a scouring effect on the ingot surface. It's steam cleaning taken to the extreme. At this point, the cleaned ingots are featureless steel planks. Turning them into rail tracks requires some formidable hardware, called rollers. In an adjacent workshop, you can see the tracks taking shape. The rollers are giant steel cylinders carefully tooled with grooves that will mold the track head and stretch the steel to that final 120-meter length. The giant tracks move back and forth, through the rollers on the floor of the plant no less than 16 times. With one new red-hot ingot hitting the floor every 5 minutes, track rolling involves a skillful bit of choreography. And this is where the dance master sits. A control cabin looking straight down onto tons of red-hot steel. Get the timing wrong and you'd end up with one heck of a pile-up. Tons of red-hot steel bent hopelessly out of shape.
If you get out of step with the rail tracks, either moving through the system or coming back, then yes, a collision is possible.
To avoid pile-ups, the controller sends half-finished tracks up a ramp to one side, allowing the next track to enter the system. Once milled to the correct shape, tracks face another trial by fire. A giant circular saw cuts them to precise lengths according to a railway's needs. The tracks are now the right length and shape, but there's a problem. The track head is too soft. A typical high-speed passenger train has a dozen carriages. Each carriage weighs 65 tons and has 8 wheels. When fully loaded, this means up to 11 tons are pressing down onto the track through each of the train's wheels. It's a force equivalent to the weight of Egypt's Great Pyramid pressing down on an area the size of a small backyard.
When you're looking to the forces which are running, which are brought onto rail day by day, these are tremendous forces.
This tremendous friction created by all that weight pressing down on the wheels and the track would soon wear out both of them. First Alpina has come up with an answer: harden the rail track head. Soaking the cooling rail track in a kind of liquid plastic called polymer knits steel molecules together in a far denser pattern than that produced by cooling in the open air. The effect of hardening the track head is to reduce the contact between track and wheel.
The contact areas of steel wheels of a train, in combination with the runaway, with the head surface of a rail, are very, very small. Only a couple of square millimeters per wheel.
The result? The wheels glide over the track head surface, and that means less friction and less wear. Back in the plant, the tracks get a final milling to make sure they're absolutely straight. And then comes the acid test. The tracks are long, they're straight, they're hard, but they're going to have to face 25 years of brutal use. So, are they safe? It's Christian's job to find out. The machines that Christian tends have one task: to spot the kind of imperfections in the steel that could cause a train crash.
In the inspection area, we check the tracks for both surface and interior faults.
At a speed of 1.5 meters per second, each new track is fed through a series of 4 different automatic inspections. Light scans check for surface imperfections. Magnets check for invisible faults in the steel. and ultrasound is used to check the inside of the track. The computer has spotted something. It's a tiny blemish in the track. Although it's small, even the slightest flaw in the composition of the steel can cause fractures or premature fatigue deep inside the track. If anything shows up, the track is diverted to a manual inspection area. The inspection must be thorough. Every scratch is closely examined. Sometimes it's only a surface abrasion, but if it isn't, the track is rejected. The folks at First Alpina take track safety very seriously.
Passengers' lives depend on these rails, and that's why inspecting them is so important.
Millions of people rely on railways worldwide. In Europe, rail travel remains one of the safest forms of transport, thanks largely to the precision engineering behind the high-speed rail track. 5 ordinary objects, 5 extraordinary stories. You're looking at a high-tech miracle, an incredible event, so familiar to most of us, we don't give it a second thought. This is a close-up view of a computer printer cartridge delivering ink to the page. These droplets occupy a tiny space, yet printer cartridges can fire millions of them a second to form extraordinarily sharp colour images. So, how do they do it? Hewlett-Packard is the world's largest computer printer manufacturer. The company plant lies just south of the US city of Portland, Oregon. 800 people work here around the clock to supply cartridges for 20 million printers worldwide. Disassembled, the cartridge looks simple enough. It's made up of 3 main components: the ink held in this reservoir, the firing chamber, and a small plate peppered with tiny nozzles. Together, as a microscope reveals, these components produce something amazing. Images and words delivered as a distinct series of tiny dots, hundreds to the square inch, many thousands to the page. To do its work, the cartridge must exercise a very precise control over one thing: a droplet of ink so small it could sit on the tip of a human hair. Computer ink is a highly engineered liquid, 80% water, 20% a blend of solvents, pigments, and a kind of liquid plastic called polymer. The balance of ingredients is crucial. Here at the ink lab, technician Melinda Pride checks for colour bleed. It's called the egg yolk test. Put a blob of yellow ink into a dish and add a drop of black. The black should hold its shape, even when the dish is agitated. After checking for colour fastness, technicians then check for colour permanence with a relentless ink-killing machine which shows no emotion and knows no mercy: the faderator. Using a battery of fluorescent lights, the faderator subjects photographs to a lifetime's daylight. In just a matter of hours, photographs are artificially aged by up to 75 years. A computer then compares their colour balance against a control chart to measure fade resistance. This batch of ink has passed the test. Ink is the cartridge's only moving part. It's pumped through tiny nozzles like these. Each cartridge has about 400 of them, set into a plate the size of a postage stamp. Like a micro machine gun, each nozzle pumps out 36,000 droplets a second. It happens so fast, it can only be measured in microseconds.
1 microsecond is a lifetime.
They call him Mr. Bubble. His job is to boil tiny drops of water inside the cartridge firing chamber. The aim, to monitor print velocity. At 2 microseconds, the ink moves in a flash.
To give you an example of how fast these things occur, a beam of light from this flashlight, when I flash the switch on, it goes 1,000 feet in 1 microsecond. So, if I aim it out the window, 1/1,000,000th of a second after I turn the light on, the head end of that beam of light is 1,000 feet away from us.
It's as hot as the sun. It explodes thousands of times a second, and you could just be sitting right beside it. More secrets from inside your computer printer next on How Do They Do It? You're looking at a mind-blowing cosmic event. Inside this printer cartridge, an electrical resistor fires bursts of energy so intense they're 7 times hotter than the sun. The heat vaporizes the ink and pushes it through the nozzle. But relax, the thermal reaction is impossibly brief, just 2/1,000,000ths of a second. You and your computer are safe from meltdown. At this micro scale, the slightest contamination could cause a cartridge engineer's worst nightmare: nozzle blockage. Here at the Droplet Break-Off Observation System, or DBOS, technician Jeffrey Langford reveals what a tiny speck of dust on the nozzle plate does to the ink flow. It isn't pretty. The ink gets blocked. The cartridge can't fire. And that's why the ink is made here. They call it the clean room, a place completely devoid of everyday contamination. No dust, no dirt, not even a speck of dandruff. It's one of the cleanest environments on Earth.
This is a Class 10 clean room, which means that there are 10 particles in every cubic foot of air.
Besides ink, the clean room is also where the nozzle plates and firing chambers are made. It's a high-tech micro-engineering operation. But when you're dressed like an astronaut, how do you recognize your fellow workers? Jeremy Donaldson gives us some tips.
After a couple of years of walking up to someone and saying, "And you are," you start to pick up on the visual clues of the eyes and just the way someone's shaped and then how they carry themselves.
Back in the main plant, it's the end of the shift, but the cartridge faces one final hurdle. Forget the faderator. This man is a cartridge killer. His job, to get cartridges printing in the hottest, most humid environments imaginable. This is a climate-controlled test chamber. If it works here, it'll work anywhere.
We emulate different printing conditions. So this is a 35 Celsius with 20% humidity. So as an example, maybe printing in Phoenix, Arizona.
And when they're through baking the cartridges, they put them on a tower and drop them.
I drop things, and I enjoy dropping things. It's a great job.
So next time you hit print, think for a moment about the miracle of engineering under the hood of your computer printer. And watch out for that thermal reaction. It's the closest any of us will ever get to a cosmic nuclear explosion. Thankfully. Behind the ordinary things that surround us in our daily lives are miraculous advances in engineering which we rarely get to see. Ingenious solutions to problems most of us never knew existed. Since this program began, the world's factories have produced around 30,000 fireworks, assembled 4,000 plasma screen televisions, forged 10,000 tons of rail track, made 150,000 ink cartridges, and ground up 57,000 tons of metal for recycling. Even the most ordinary objects often have extraordinary stories to tell. We only have to watch and listen.